Here we have a theorem that tells us how a function's derivative is related to the inverse function. Assuming you have a differentiable and invertible function, it turns out the way you take the derivative of the inverse function is you take 1 over the derivative of your given function evaluated at the inverse function. So looks like a lot of work, but we'll use this to derive a couple of formulas, or at least one formula. But we'll also see there is a way that this is useful, especially if you don't know what the inverse function is. So let me give you a little motivation of where this comes from. We know this property, that f of f inverse of x, that's going to equal x when you have inverse functions. And so I'll take the derivative of this equation, and here's what I get. The derivative of f inverse of x is equal to the derivative of x. And so here we're going to use a chain rule. We've got an outside function of f, an inside function of f inverse. So you start on the outside, you take the derivative of f, put the inverse function, put the inside function back inside, and you multiply by the derivative of that inside function. And that's our way of writing the derivative of the inverse. We put the parentheses so we don't get confused as to where that prime is. So there's your derivative using the chain rule on the left hand side, and this is just 1. And now I can solve for the inverse derivative is 1 over this, 1 over f prime of f inverse of x. So that's the formula. You can sort of see where that might come from, and let's use it. Show you a couple of places where it's useful. So I want to find, for this function 2x plus cosine x, I want to find the derivative of its inverse at 1. Now the first question is, does this function have an inverse? To have an inverse, it needs to be strictly increasing or strictly decreasing, and I know cosine is not strictly increasing, cosine is oscillating. But it turns out that 2x is increasing fast enough so that even though cosine is oscillating, what it does to your graph of cosine of 2x is it makes it sort of oscillate, but never decreases. It just sort of bends back and forth. So this is a strictly increasing function. And so I can presumably find the inverse, which you can't. I mean, this is not a function that I can go through the inverse process and find what the inverse is. So we actually don't know what the inverse of this is. I could sketch its graph and that sort of thing, but I don't know what the inverse is. But I still want to calculate the derivative of the inverse and evaluate that at 1. By the theorem above, that's equal to 1 over the derivative of my function here that I'm given, evaluated at my inverse function at 1. So at least I've reduced it now to just finding, if I can find that value, then I've got my derivative of my inverse. Well, let's see, that value, we're going to solve it like we do with the inverse trig functions. I've got this. I want to know what f inverse of 1 is equal to. Let's say it's equal to a, some number. Well, I'm going to take f of both sides of this. That's a 1. I'll take f of that. And so this side, since I have f of f inverse of 1, this side is just 1. And so what I've reduced it to is trying to find the number a such that when I plug it into this function, I get 1. Now that's not always an easy thing to do for a function that's got a mix of trig and polynomials, but in this particular one I can guess the answer because I see that if I plug in 0, I get cosine of 0, which is 1, 2 times 0, which is 0. So I can see that f of 0 happens to equal 1. So therefore, since this is a strictly increasing function, meaning there's only one place that you're going to get 0, there's only one place you're going to get a 1 out of it. So that tells me that a has to be 0. So back up here, that says that I've calculated what f inverse of 1 is. That's 0. So this reduces to finding f prime and evaluating it at 0. Well, f prime, we can do that. It's not a difficult problem there. That's just 2 minus sine x. And so if I plug 0 into this, I can see that I'm going to get 2. So I don't know what the inverse function is, but I know that the inverse function is related to the function itself, and its derivative is related to the function itself in this way, so that I can calculate this particular value. Now you give me another value and I might not be able to do it unless it happens to be one that I can do like I did here and sort of guess what the value is that gives me that inverse value. So it would have to be something nice like a pi or pi over 2, and then it'd have to be kind of set up to work out. But just shows you that there are some places where I can apply this. I couldn't do this otherwise, because I can't find that inverse. And here's another place where I can derive a formula that we'll be using for the rest of the semester. I want to know what the derivative of natural log of x is. And so I'm going to call that my inverse function. That's the inverse of e to the x, right? We said that earlier. So what I'm going to do is, starting with f of x equal e to the x, I'm going to try to take the derivative of natural log. Well, according to our formula, that's equal to 1 over the derivative of f, and that's evaluated at my f inverse. Well, the derivative of f is just e to the x, and f inverse is natural log of x, so this ends up being 1 over e to the x evaluated at f inverse. But as I said, e to the f inverse is really natural log, and so what I get is e of natural log of x is just x. So that says the derivative of natural log of x is 1 over x. Like I said, that's something we'll use throughout the rest of the course. I can derive this in another way, just to doubly verify. I'm going to use the inverse function here by taking e of both sides, and I get e to the y equals e to the natural log of x. And now that would be then that e to the y is x. Now I'll take the derivative of both sides with respect to x, and here's what I get. On this side, I'm trying to take the derivative of a function of y with respect to x. These variables don't match up, so I take the derivative first with respect to y. Well, the derivative of e to the y with respect to y is e to the y, then you tack on dy dx. And then the derivative of x is 1, so I get dy dx is 1 over e to the y. But right above here, I can see that e to the y is x, so that tells me that dy dx is 1 over x. So two ways to show that the derivative of natural log is 1 over x. One using the definition, using the theorem about inverse functions. The other one using implicit differentiation. So the important part is we can use this idea on inverse functions to help me derive formulas for functions based on the function they're the inverses of. So it's important to know some theorems to expand the number of functions we can take derivatives of.